One of the last examples that I'd like to do with geometric series is what I think is a really cool application of them to a topic that you've learned about long ago but may have forgotten. So one thing that you may have learned is that we have two different ways of representing numbers. Sometimes we like to represent numbers as fractions, and other times we like to represent numbers as decimals. Now, it is a fact that if you have a number that can be represented as a fraction, say a half or a third are good examples here, then one of two behaviors will happen when you translate that fraction into a decimal. Either the decimal is going to terminate, like the 1/2 example, the answer is 0.5, and then we stop writing numbers, or we get examples like 1/3, where eventually a pattern emerges in the digits of the decimal expansion, and we put that little bar over the top of the decimal to indicate that the decimal never terminates, but this selection of digits repeats forever and ever and ever. Numbers that can be represented as a fraction of integers are called rational numbers, and those are precisely the decimals that either terminate or eventually have a pattern. Note that that isn't all numbers that can exist. Examples like pi exist, which are decimals that go on forever and ever and ever. But in representing a number like pi as a decimal, we never reach a point in the decimal representation of that number where we find a chunk of digits that just repeats over and over and over again. So we don't get all real numbers in this way, but we get a special selection of numbers called rational numbers. Again, rational numbers are those that can be represented as a fraction of integers. And so it's no coincidence that we call rational functions functions that are a ratio of two polynomials. We're in fact meaning to draw a similarity between rational functions and rational numbers. Now, where geometric series come into this is that it's a very easy process to take a fraction and find its decimal representation. We would do that process with long division, and long division is something that you learn about 4th grade in the United States. So a relatively simple mathematical process. However, there's a different question, which is if I have a decimal that is eventually a repeating decimal, how do I find the rational number that corresponds to that decimal? That's actually a much more difficult question that we need geometric series to answer. And I love this type of problem when it arises in mathematics, where we have a process that goes both ways. Fractions are the same as these particular decimals. And going from one side to the other, i.e. fractions to decimals, is a really easy thing. But going backward is significantly more complicated. That type of situation that occurs in mathematics is called a trapdoor function. And it's super interesting, and trapdoor functions are in fact how all internet security works these days. So trapdoor functions, processes that are easy to do in one direction and very difficult to undo, are super fundamental to really interesting things on Earth. And decimal representations of fractions is one example of a trapdoor function. Let's work with an example to show you how geometric series come up in this particular context. Let's take a look at the decimal 0.234234,234, or in other words, the decimal 0.234 repeating. Well, if we want to write this number as a fraction, as I've indicated, we're going to need to use geometric series. And in order to use the tools that we've developed for geometric series, we need to take this decimal and make it look like a geometric series. Let's think of that 234,234,234. Let's color code it, and let's break up this decimal as a sum. We first peel off the 0.234 portion of the decimal, and then to obtain the blue portion of the decimal, we have to put zeros in the spots where the red digits are, so 0, 0, 0, and then the 234, and leave the whole rest of the 0.234 repeating for later on. Similarly, if we want to access just the green 234 in this process, we'll put zeros for each of the digits in the red and blue parts of the decimal, then have our 234, and leave everything else in that repeating fraction for the next term in the sum. So we're going to represent this decimal as the sum of these decimals. Now the benefit of these decimals is that they are finite, and finite decimals like 0.5 are very easy to convert to fractions. 0.5 would just be a 5 over 10, or in other words, the 1/2 that we started with. So if we'd like to take the red, blue, and green finite decimals that we've written on this side of the expression, we can convert them to fractions by just taking the number that we're seeing and dividing by the proper power of 10. So 0.234 would be 234 1,000ths. Since I have 6 digits over here on the left of 0.000234, I should have a 10 to the 6th, or a 1,000 times a 1,000. And last but not least, over here I've got 9 digits in the green decimal expansion, so what I'm looking at is 234 over 10 to the 9th power. Writing this decimal out differently to help us notice a pattern, we start to see things in a way that we're used to for geometric series. We can easily identify the first term in our geometric series as the red portion of the sum that we have right here, 234 over 1,000. And as we're moving from one term to another, in order to shift those digits over 3 places, we're multiplying by a 1 over 10 to the 3rd power, making our common ratio 1 over 1,000. Because 1 over 1,000 is smaller than 1, that's the criteria for us to have a convergent geometric series. This series, which has exactly the same value as this decimal, is a convergent geometric series, and it converges to the first term divided by 1 minus the ratio. And when you do that double fraction arithmetic, you end up with a value of 234 999ths, which is reducible, but this is the first form that we would see it in and is a perfectly acceptable answer. This is a fractional representation of 0.234 repeating. And this trick of identifying what is the fundamental portion that repeats over and over again and rewriting the repeating part as shifting copies of the same first term is a trick that will always work to find a fractional equivalent of a repeating decimal.